Okay, I sound kind of a little bit too loud. Is it okay at the back? Still good? All right, so today we're going to start talking about the last milestone, milestone 4, which is algorithmic. Okay, so it builds on top of milestone 3, but it's a more open-ended algorithm. There's no GUI component. You can build one if you want, but you don't have to. Okay, so what is milestone 4 about? It's a variation on a classic computational problem called traveling salesman. Who has heard of the traveling salesman problem? Anybody? Okay, so quite a few people. Okay, so there are many variations of the traveling salesman problem. This is one that we made up for this course. So it starts off with you got to pick up a truck. Okay, so you're optimizing a delivery route, and you've got multiple depots where trucks have been left, the previous night by your company. So you get to pick which one you want to pick your truck up from, and then you got a whole bunch of deliveries to make. Okay, so you've got N deliveries to make, and a delivery is you got to pick something up, which is shown in green here. So for example, I've got to pick something up from this location. That's my delivery A. And I've got to drop it off to someplace, which is over here. Okay, so that's what I need to do for delivery A. Let's see if I can get a different color here. Okay, and I've got delivery B to make, so I gotta pick it up first. So I gotta pick up delivery B here, and I gotta take it there. Okay? So to come up with a legal route, I gotta get my truck from one of these depots. I can pick which one. And then I've got to go pick up every one of these packages. There are 4 of them, and I'm going to drop them off. And I have to pick them up before I drop it off. Okay? So here I've got number of deliveries I have to make, which we're going to call N is 4. And every delivery is to an intersection. And you've got D courier depots. So these are choices of where you pick your truck up from and where you leave it at the end of your shift. Okay, so in this example, I've got D equals 3. I've got 3 different spots where I can pick up and drop off trucks. Okay, so what you want to do is return a low travel time path. It has to make all the deliveries. So you got to go through all these intersections. And you have to go through them in an order where you've actually picked up whatever you're going to drop off before you go to the drop-off location. So in order to make this delivery, I've got to pick up the package A, before I drive over to drop it off. And then at the end of my route, I've got to basically, so maybe I start here, I make that delivery. If that was the only delivery I had to make, then I could drop my truck off at some other depot. So I can leave, my company's got lots of trucks, they don't care if I pick up and return at the end at the same spot. Now what I showed here isn't a full route because I didn't make all my deliveries. If I only make one delivery, I'm gonna get fired. Yeah, so let's go to B09. And
is it possible for me to go A up and then D up and then D down and then A down, or?
A up, okay, so the question was, could you go A up and then B up? You're saying, could you just do this? Go to A, then go pick up B, is that right? And then go over here, drop off A, and then maybe go drop off B. Is that right? Yeah, that's fine. Okay, so that's actually the problem is you actually want to reorder things. Okay, so a very simple solution is whatever order we give you the deliveries in, you just go do that. You're not a very good delivery person, right? You just take your list of deliveries and you just do them from start to finish without ever looking to see like what are all the deliveries I need to make. Are they 2 people beside each other on the same street? Maybe I should make them both at the same time. So you're going to try to optimize this order. So a possible solution. Well, let's see, is this a possible solution? So let me change my pen color to my favorite red color. Okay, so here I'm basically saying I'm going to pick my truck up there. And then I'm going to go to make my B drop off. Then I'm going to pick up package D. Then I'm going to go way over here. Okay, I'm going to drop off A. Then I'm going to pick up C, pick up B, drop off D, and so on. Okay, then I'll drop off C, then I'll pick up A, and then I'll go to drop off my truck at the very end. Would this pass, is this a legal solution? Okay, so if you did this, would your bosses be happy? What do you think? So I see C09, you're shaking your head. Why do you not like this solution? I'm going to turn on your mic. Sorry, okay, I'm trying to figure out the game. Okay, try it again. Yeah. So this isn't a legal drop-off order, okay? I'm doing crazy stuff. Like basically I'm trying to drop off B before I've actually picked up B. It's okay if I go through this intersection, just drive by, but I can't say I'm actually making the delivery because I haven't actually picked up the package yet. So this wouldn't be a legal delivery order. So not all orders in which you visit things kind of make sense. You have to do things in an order that makes sense. Okay? So what I've shown here, well, take a look at this one. Does this one look legal? So I start here at a certain depot, I pick up D, I drop off D, I pick up B, I pick up C, I go way out here to Scarborough, I drop off C, pick up A on the way back, then I drop off B, drop off A, and then leave the truck at a different depot. Does this look legal? Okay, so people are giving me a thumbs up. Yeah, so that one's legal. Okay, so the output of your algorithm, I'm about to release the milestones. I haven't released the code yet, but it'll come out in the next day or so, is going to be essentially a vector of paths, okay, what we call subpaths. So a subpath is basically what your milestone 3 algorithm gives you. Subpath is you go from a start intersection to an end intersection. What are all the street segments? This is a more complicated delivery route. So instead of just giving us one of those subpaths, you're going to give us a bunch. You're going to tell us, okay, I want to start at this depot, go to this intersection, here's how I go there, these street segments. Then I want to go from this intersection to this intersection, and I want to follow these 2 street segments. So you're going to give us a vector of these little pieces of solution, and together it gives us the whole answer. Okay, so you're going to build on top of your milestone 3 algorithm. If you don't get your milestone 3 algorithm fully working, it's okay. We're going to give you a simple pathfinding algorithm that you can call. All right, so you won't get stuck if your pathfinding algorithm doesn't work. We'll just give you one that you can call. Okay. All right, so whenever you tackle something like this, we say get something simple working first. So I'm going to give you a simple solution to this. So what this is doing is basically saying let's just create a legal solution quickly by reusing our milestone 3 solution, or like I said, if you didn't get that going well, you can use a simple one that we'll give you. So what am I doing here? I'm basically I'm going to do things in the exact order that I was given them. So I'm like the delivery person who never reads ahead. I'm just looking at my delivery list and I'm just doing it one item at a time. Okay, so I say, find me the path from the first depot. So maybe there are like 5 places I could pick up a truck, or in this case, there were 3. I'm not even going to look at the next 2. I'm just going to take whatever one's listed first, that's where I'm going. Okay, so I don't read very far through instructions. So I'm going to start at the first depot, and I'm going to go to the first pickup. And this is how we give you the problem. We give you a vector of depots, and we give you a vector of deliveries. Every delivery has a pickup intersection and a drop-off intersection. So I just say, start at the first depot you gave me and go to the first pickup location. And I need to compute a path. I need to tell you how I got there. So I'm going to call find path, which you just wrote, and I'll get a path from that. Okay, now I'm going to complete all these deliveries in order. I'm just going to say, okay, from that first delivery, I want to go from the pickup location, that's a certain intersection, to the drop-off location. So between those 2 intersections, find me the path and just add it into my solution. And that's made 1 delivery. I now need to go pick up the next delivery. So from where I am right now, I just dropped off a package. I want to get the path to the next package I'm supposed to pick up. Okay, call my find path algorithm again, add that into my solution, keep doing this until basically I've made all the deliveries. Okay, or almost all the deliveries. I've got one more to make. I basically take that last delivery that I picked up, drop it off, and then basically I'm gonna go back to the first depot. Okay, so I'm at some drop-off location. I go back to the first depot where you told me I could pick up and drop off a truck. I'm done. Okay, so does everybody understand this solution? Does it look legal? Does this look like if you did this, it'll pass the auto tester for this milestone? The first thing it's going to do is it's going to check, is your solution legal? So what do you think? Does this look legal or not? Okay, so I'm going to get a thumbs up. Yeah, so it's legal. So this is a quick way to get a solution going. Do you think it's going to be very good? Is this going to be a good solution? What do you think? I see C07 shaking your head. So yeah, this is not going to be a very good solution. So even on my little problem that I gave you here with 3 depots and 4 pickups and drop-offs, let's see what it would do. Okay, so I just said I'm going to start at the first depot. So that one. Don't even look at the other 2. And I'm going to go to the first pickup, which is way over halfway across the city. From there, I'm going to go back and drop off. It's supposed to be dropped off here, so I do that. I'm going all the way across the city again. Go pick up my next pickup, which is up here. Go drop it off, which is way down south. Go pick up the next thing, which is here. Go all the way across the city to drop it off. Go make my next pickup, which is here. Drop it off, which is pretty close. That's good. And then I go back to this depot, even though this one looked like it was closer. So it works. Doesn't look very optimized. You can see we're going back and forth on Highway 401 a lot. So probably my boss is not going to be too happy with my efficiency. Okay, so there's a lot of ways to travel here, but it is legal. Okay, so a more logical solution is, try not to do so much driving, right? You're near something, try to do that. So I might start at this depot. It's a little more centrally located. I pick up this package. I can immediately drop it off. I pick up this package. I'm pretty close to another pickup, so I'm just going to get another package. Okay, and then I go all the way over here to make a drop off. I make another pickup on the way back, make this drop off, make my final drop off, and I leave the truck at a different depot because I'm pretty close to another drop off location. So it's a lot better. Okay, so clearly even for this relatively small problem, we can do a lot better. Okay, so you need to optimize the delivery order. It's actually a perfectly reasonable thing to do to just get that first solution that I showed you, because it would get some marks, right? So you get it going, you go, hey, I got a legal solution, but then you want to do more. Try to optimize the delivery order. Okay, so one way you could do that is, what if we just try everything? Okay, there's a bunch of delivery orders, let's just check them all. So, and then we'll generate all the possible solutions. We're going to write a function that figures out the travel time for a given solution, and we'll just return whatever one gives the best answer. So let's see how fast that is. Okay, so how many combinations? Let's say I want to do this. Let's see if anybody can guess this. So the way I've set up this problem, can you bound how many solutions there are? Okay, so I've got n intersections, I've got d depots. Maybe it's n times d solutions. Maybe it's n squared solutions. Maybe it's hard to say. If anybody wants to take a crack at it, go for it. And this is a very reasonable way to attack a problem. Okay, so I'm asked to optimize this. Maybe I can just check all possible solutions. And if that's pretty fast, that's a pretty good way to do it. Okay, so I'm going to go to C07. Let's say you got an idea. Maybe that's going to turn your mic on. Okay, go ahead. Yeah.
A couple of different combinations. We can see the first one. The first place to go to, we have 3 options because we can go to any of the 3 pickups.
Right. Okay.
The second one, we can go to any of the rest of the pickup and one drop down. So we multiply by another 3. Then the third one, and go on. We see how many options it multiplies.
Okay. Okay, so you said the first choice, let's do it with variables. So we have D depots. You're saying first we have D choices of where do we start by picking up our truck. Is that right? Okay, and then I have n pickups and drop-offs. So how many choices do I have for that second thing?
One.
Right, so I have probably actually n, because of the way I've set up, the problem, I actually got n choices for the second thing. So I got d times n, and all I've done so far is get my truck and make my first pickup. Now my next decision, how many choices do I have?
Also, you need to record what good deliveries you have got. And if you don't any drop down, you record the drop it down. So on the third one, you record on the what you have.
Yeah.
And also, and the pickup you have to visit, then those are the options.
Right, so you're saying that basically the number of options that I might have on the second and third and fourth decision can vary depending on what's legal. Is that right? So you have to kind of keep track of it. But you started off with D decisions to make for the first thing, D choices for the first decision, N for the second decision, and maybe variable for the third. So that makes sense. Does it sound like a lot of decisions or not? Is this sounding like the number of solutions is going to be large or is going to be relatively small? So what do you think? Large or small?
It would be, I think, a factorial, like after you have D first, and then you have N second, and then the third one, you can either drop off as well as go to N minus one remaining pickup.
Yeah.
That would be another N, and then after that, you will have N minus one.
Right.
And then N minus two, you get some kind of factorial.
Okay, so a good insight. So this looks like a factorial, which grows really fast. Okay, so that sounds kind of bad for evaluating all the options. So we start off, we got D of these truck depots. We could pick any one. For the deliveries, we've got N pickups and N drop-offs. So 2N, if we combine those, 2N pickup plus drop-off locations. And then at the very end, so I guess that's our input. The first thing we do is we pick one of those D starting locations. Then we have to pick up, there are N legal choices we can make after that. We could go to any one of the pickup locations. And then the number of legal choices varies depending on how many things we have in our truck, right? We could pick another thing up or we could drop off something that's on the truck. To simplify things, I'm just going to say my algorithm just generates all the possibilities and checks whether they're legal or not afterwards. You could say, well, I'm going to be a little more clever. I'm not going to generate the illegal possibilities and you'll get a slightly lower number, but it's a little easier to do it this way. So let's just say I'm going to generate all the possibilities. So any one of those two N intersections, maybe a pickup, maybe a drop off, and then I'll check if it's legal. Okay, so if I do it that way, I've got 2N choices for my second decision. And then I've gone to one of these intersections, so now I've got 2N minus 1 choices for the next one and so on. I repeat that to the last delivery, and at the end, I actually can just drop off at the closest depot. There's no real point in evaluating other choices. I'm done, I'll just go whichever place is closest. Okay, but if I multiply this out, it's a big number. It's D for where do I start? Then 2N options of what intersection to go to. Now, N of those are illegal, but my algorithm doesn't really think about that. And then every time I make a pickup or a drop off, my number of choices goes down by 1. But yeah, this is factorial. So it's D times 2 to the N factorial. Maybe you could code it in a more tricky way, and you might be able to get this 2 to the N factorial down to N factorial. Okay, but it's still a really big number, so it doesn't matter too much for our purposes. Okay, so let's just plug some numbers in. So let's say we have 10 depots and 100 pickups and drop-offs to make. And the biggest problems we give you are going to be this big or actually a bit bigger. Okay, so they have more than 100 pickups and drop-offs to do. So if I plug these numbers in, I get 10 times 2N factorial is 10 to the 377. That seems kind of big. What do you think? Does that seem pretty big? Okay, but computers are really fast. So what do you think? Maybe fast enough computers are going to make it feasible. So who thinks this is going to still be okay? Because those UG machines are pretty fast. Okay, see lots of head shaking. Okay, what if I multi-thread it? I use all the cores. I got 4 cores. What if I use all 4 cores? Is it going to save me? Okay, what if I code it really efficiently? Seem a little skeptical. Okay, so yes, this is a big number, and the most straightforward way to do this is that if I want to find what's the travel time of each of these things, I'm just going to invoke my find path algorithm to get all the little subpaths. Okay, and I have to for each of these long delivery routes, I actually have to invoke my find path algorithm a bunch of times, actually 2n plus 1 times to connect everything up. So depends on how fast my find path algorithm is. But a pretty good implementation is about 0.1 seconds. Okay, so pretty fast, but it's not a negligible amount of time. So if I multiply all that out, you know, this number of solutions, that's what's really killing me. And then every one of them needs 201 invocations of my find path algorithm, which took 1/10 of a second. So I get this many seconds, 1.6 times 10 to the 378. Okay, seems like a lot, right? That seems like a lot compared to the time limit. The lifetime of the universe is estimated to be 14 times 10 to the 9th years. Okay, so yeah, you're going to be waiting a long time to graduate. Okay, like an uncountable number of lifetimes of the universe in order to graduate. So you can't do an exhaustive algorithm. We're never going to be able to do this. Okay, so we're solving a variation of the traveling salesman problem, which is what's called a computationally hard problem. What makes the traveling salesman problem hard is that if you actually have a sub-solution, so let's say you find a good delivery route for the first 50 intersections, first 50 deliveries, and somebody adds one more delivery. You can't say, take my solution for the first 50, combine it with just the best thing to do for that last one, and that the answer is still the best. Okay, so you can't build up your solutions a little bit at a time and have any guarantee that you've got the best solution. That's actually different from shortest path. In shortest path, if you actually look at Dijkstra's algorithm, which we developed over the last few lectures, once we find the shortest path to a node, we can actually use that shortest path to find the shortest path to the nodes next to it. That's actually what makes Dijkstra's algorithm efficient. It's kind of finding the shortest path to nodes, and then it finds from those nodes what's the shortest path to the next set. That doesn't work for the traveling salesman. It turns out if you put another delivery in, maybe you have to reorder all the deliveries you already did in order to get the best solution. So it's harder. So computationally hard means there's no guaranteed optimal, so guaranteed to have the best travel time in this case, solution that can be found in polynomial time. Okay, so what does that mean? It means that the order of any solution that is guaranteed to be optimal, guaranteed to get the best possible answer, must be greater than n to the k for any k. Okay, so not n squared, not n cubed, not n to the 4th. If I say, what about n to the 283? For some sufficiently big n, that's not enough, right? It's like, nope, got to be more than n to the 512k. In fact, there's no k you can choose that will bound the complexity of an optimal algorithm. What that means is that the solution, an optimal algorithm has to be at least exponential. Okay, it has to be at least 2 to the n, which is big, right? So it means I add one more delivery and the runtime of my optimal solution doubles. So that's a lot. Okay, so it turns out there are many, many problems that are computationally hard, and those are generally the interesting ones that people spend a lot of time researching. You need to use heuristics to solve them. So heuristic just means good idea. I can't guarantee that this gets the optimal answer. No one can. But it seems like a good idea, and maybe I'll combine a few good ideas and I'll tend to get a good answer. Okay, so, and there are lots of these. So I showed you last class pictures of, big FPGAs and pictures of Cerebrus's, 850,000 processor, wafer that they're using for deep learning training. So one of routing, connecting everything together, uses shortest path algorithms. So it's using one of the algorithms that, the algorithm that you're developing for milestone 3 is related to that. There's another problem in integrated circuit design, which is choose where you put all the bits of circuitry. Okay, so that's called placement, and that is related to the traveling salesman problem. It is computationally hard. So for Cerebrus, they're choosing where to put 850,000 processors. And there's no optimal solution because it is related to the traveling salesman problem. And you can see, okay, now that is a really big N. We're talking about n equals 100 was going to take us forever. Well, that's n equals 850,000. So you have to find clever heuristics because how well you place those processors on Cerie versus wafer is going to affect essentially how efficient they are at computing. Like how well can they exchange information? If there are lots of things that need to talk that are far apart, it's like a bad delivery route and the whole system slows down. But it's not the only one. So drug design, when they're trying to figure out how proteins will actually fold, that is another optimization problem that is computationally hard. And it turns out modeling how proteins fold is key to figuring out how drugs will work. And then obviously what we're doing here, transportation network design. So deciding how to make a city, how to actually optimize an Amazon warehouse delivery structure, deliveries within a city. The problem I'm showing you is actually a realistic problem that people write programs to solve for actual truck deliveries and picking up items in Amazon warehouses and so on. Okay, so has anybody here heard of Stephen Cook? So at least one person. Do you want to tell us who Stephen Cook is, or am I going to put you on the spot too much? I'll respect your decision. So, yeah, so I'm going to give Ken the mic. Go ahead, Ken.
Once I say that, I'm reading the slide.
Oh, you're reading the slide.
But he had a very interesting path in his career where he had a number of challenges that were kind of major, right?
Yes. Okay, we'll clear these. So yes, he's a U of T prof in computer science. Whoops, sorry. He's a U of T prof in computer science, so not far from where we're sitting right now. His research area is npcomplete problems, which are basically, I talked about computationally hard problems. Those can be divided into even finer categories, but np-complete problems are a major class of computationally hard problems. So np-complete basically is almost a synonym for computationally hard. It means no polynomial time solution is known on conventional computers. Okay, so maybe quantum computers in some cases could do it in polynomial time, but not conventional computers. Okay, what did he prove? So he proved that if a method to solve any of these problems in polynomial time is found, okay, so integrated circuit placement, I just talked about that, optimizing courier delivery route, drug optimization by modeling protein folding, any of those, if you find a polynomial time solution, then all of the problems in this class, which is basically most of these interesting computationally hard problems, all can use that. Okay, they can all be transformed into each other in polynomial time. So if you find one polynomial time algorithm to solve one of these problems, you have actually solved them all. Okay? So he showed this is the case. He could not show that no polynomial time algorithm exists. He just showed that if you ever find one, you basically just solved most of the world's interesting computational problems, much more efficiently than ever has been done before. So this is the search of proving. So no one has ever found a polynomial time problem for these algorithms, for these problems. But no one's been able to prove that one doesn't exist. Okay, so this is called the P versus NP, the polynomial time class of algorithms versus the non-polynomial class of problems. So if you are kind of a risk taker, you could go to grad school and you could try to prove that P equals NP or P is not equal to NP. Because right now, everybody thinks that there is no polynomial time algorithm because no one's ever found it, but they haven't been able to prove it doesn't exist. So if you're a gambler, you could say, I'm going to be the one who proves it doesn't exist, or I'm going to find it. Although it is kind of a high-risk strategy because no one's been able to solve it yet, so there is a chance of an infinite grad degree too. But this is the most famous open problem in computer science. Okay, so as Dr. Tallman said, his path in academia is actually kind of interesting. So Professor Cook started his career at Berkeley. He was a professor there. When you become a professor, it's a kind of an odd job, actually. So for 6 years, you work a lot, and you don't get much feedback. You're just trying to publish, build a research group, teach as well, but frankly, the research is the part that research universities mostly look at. And at the end of that 6 years, there's a committee that's formed and they send letters out to experts in your field and they say, what do you think of this person? And the letters come back and they hopefully say, this person is fantastic, you know, hire him or her forever. Okay, so if it comes back, it all looks good, you're given tenure, which basically means a job for life. If it comes back and they say, yeah, I'm not so sure about this person, you're denied tenure, which means basically you have to leave the university, okay? So it's really odd, right? There aren't many jobs where they say, come in, work like crazy for 6 years, we won't really tell you how you're doing very much, and then we'll either give you a job for life or we'll fire you. Like, you're not gonna go out and interview with a company where they say that's their career path. But that is the path that, like, major research universities. So after 6 years of hard work, he was denied tenure by UC Berkeley. Which has got to be a very difficult thing because you've been working hard for 6 years and it didn't work out. But he didn't let it get him down. In 1971, he actually published his most famous paper, this paper that pointed out that if there's a polynomial time algorithm, all of these problems can be reduced to each other and you solve them all. So he created this field of P versus NP, showed that existed. And actually won computer science's highest award in 1982 for it. And he did this at U of T. So he was denied tenure at Berkeley. He came to U of T. So like, I still want to be a prof. I'm going to try again. Okay. And it went very well. Won computer sciences Nobel Prize, basically. And apparently, after this happened, Berkeley phoned him up to say, you know what, if you want to come back, we're going to give you tenure now. Right. So although he declined. I'm not sure how polite he was about it, but he kind of this like a sort of a revenge fantasy of like place that like told you couldn't get tenure, you know, phones you up years later after you won the highest award in the field to say, well, now maybe we made a mistake. Okay, so anyway, it's an interesting story in not giving up. Right, so pretty difficult situation that he obviously rose above. And it's one of the things that U of T is very proud of is that for complexity, U of T has been one of the strong universities researching this because of the work started by Dr. Cook. Okay, so let's talk about heuristic algorithms. So no perfect solution for this one. All you can do is kind of heuristics. Okay, so what can we do? So our very first heuristic, like heuristic 0, was we're just going to go in the order that we were told. Start at depot 0, go to pick up 0, and just keep going. It'll work. It's not going to be very good. What can we do that's better? So any ideas? So let's see. B12 is, or E12. E12, did you buzz in, or is this a leftover from before? It's a leftover, or? No, it's a leftover. Okay. Anybody want to take a shot at this? How would you attack this? Okay, so B09, I see, or actually D13. So D13, I think you buzzed in first. What do you think?
For all of the current multiple choices and just choose the best one and keep exploring only the best one.
Yeah, so, okay, so good idea. So the idea is, let's just look at what's legal right now and just pick the very next thing we could do. What's the best thing we could do right now? We're not going to worry about whether it's best overall, it's just the looks good in terms of the immediate future. So yeah, it's a good idea. So I'm actually going to do two variations of that. The first one I think is a little bit less smart than what you just suggested. So we'll go through it quickly and then go to what you suggested, which is a little smarter. So I could go from any depot to the nearest pickup. Okay, so I'm going to check all the depots, and then I'm going to go to whatever pickup's closest to them. And while I still have packages to deliver, I'm going to drop off a package, the package that I just picked up, and then I'm going to go to the closest pickup. Okay? And then at the end, I'm going to go to the nearest depot. So let's see if this is fast enough. So this first decision, I have to check what's the minimum distance from any depot to any pickup. So that's D times N choices. Then I have to go through N iterations of this loop to make all my pickups and drop-offs. And this is easy, but this involves a choice. I need to look at what's my distance or travel time to all of the pickups that are left. So that's order N. Okay, so N times through the loop, and I do order N calculation here. So that's going to be N squared. And at the very end, go to the nearest depot. Well, I know where I am. I just check all the depots. That's order D. Okay, so if I write that out, I just go, okay, that's d times n plus n squared plus d. In complexity, you can always drop the lower powers. So I can drop this order d, because it's a lower power than the other stuff, and I'm left with order d times n plus n squared. Now, all the problems are going to give you the number of pickups and drop-offs is more than the depots, so this n squared is the important thing. Okay, so n squared is actually a lot worse than Dijkstra's algorithm. Or Dijkstra's algorithm was n log n. So n squared might look kind of bad, but it is if n gets into like 100,000 or 1 million. But we're not going to ask you to make to deliver 1 million packages inside Toronto, because probably no truck driver is going to be able to handle that in a shift. You get to your shift and you find there's 1 million deliveries to make, like they're probably trying to fire you, right? That's like constructive dismissal. So n is going to be more like 100, 200, where n squared is not too bad. So let's see. Let me activate your microphone here. Yeah, go ahead.
A few quick questions. So first of all, are we going to do this in Toronto only, or are we going to do Tokyo and New York as well? For multiple forms?
It's not just Toronto, okay? So we'll test you on multiple cities. We'll test you on Toronto, in London, and in the private test cases, we're going to test you on New York, okay? Does that answer your question? We could test you on Tokyo. Your algorithm should work there, but usually we don't, okay? Yeah.
And one more quick question. Can we reprocess it and get rid of the d times n?
So you can do pre-processing and load map as long as your load map still passes the time test. So you can't do like an arbitrary amount of processing where you say, I'm going to pre-compute every possible set of deliveries you might ever ask for. That set of deliveries is enormous. So yeah, if you can think of things you can pre-process that are helpful, you can do it. But you won't know what the intersections you're trying to make deliveries are before you do the pre-processing. Does that answer your question? Yeah. Okay. Okay, so basically this will be fast enough. N squared is, again, not as fast as Dijkstra, but for n equals 10, 100, 200, this is going to be okay. But let's just try to check. Okay, so, well, I guess it depends, is this fast enough or not? It could be good enough. N squared is not that bad, but it depends on how big our constant is and how much time we give you. So we're going to give you 50 seconds, okay, to optimize. So even if n equals 200, you've got 50 seconds. So let's check if that's enough. So the very first decision, and basically the answer is it depends on what you do. So let's look at this first thing. We're trying to find from any depot to the nearest pickup, trying to make our first decision, and we're trying to pick the depot and the pickup that will lead to the shortest first travel, okay? So, and the number of choices are d times n. Okay, so here's my little test case with 4 depots, or 3 depots and 4 pickups. And from this depot, I could go to any of my 4 pickups. From this depot, I could go to any of my 4 pickups. From this depot, I could go to any of my 4 pickups. Okay, so I have 12 different travel paths that could be my first step. Okay, and in general, I'm going to have d times n travel paths that would be our first step. Okay, so and the idea is that once I find, so I look at all of these, once I find the shortest travel path, let's say it's this one, that makes the decision of where I start and where I go first. Okay, so I'm going to start at this depot and go to that pickup. But in order to figure that out, I had to invoke my find path algorithm. Well, let's say I do invoke my find path algorithm from every depot, so from 3 depots, and I go to each of these 4 intersections. So 12 different find paths. 12 isn't too bad, but for the larger numbers that we're going to test you on, oops, see if I can get rid of the zoom thing. It's going to be a problem, okay? If we have n equals 100, and D equals 10, we've got 1,000 find path calls. And if each of our find paths takes 0.1 seconds, which is pretty good, this is 100 seconds. We're not going to give you 100 seconds. We're going to give you 50. And you've only gone through the first step of your algorithm. Okay? Let's go back here. This was just the first step. Okay, so the best way to find what would be the travel time between each of these choices and pick the best one would be to call find path, but it's going to be too slow. So what should we do instead? All right, so I'm going to throw this animation again. Okay, so what could I do that's better? Okay, so I'm going to go to C09. And let's just make sure I've got. Okay. Okay, so you're basically saying don't use find path to figure out, what's the first thing you do because it's just too slow. But we do know where all these intersections are. We know they're lat long, so we could find the distance in between them. And you're saying maybe we can use that geometric information somehow to decide where to go first. Is that right? Maybe look at the average of all the intersections, find the depot that's closest to that. Is that what you're saying? Okay. Yeah, so this is a good idea. So basically, if we used find path with even the simple algorithm, it's going to take too long to evaluate the choices. So this just basically walks through that. So if I used find path on every one of these choices, and I go through calculating how long this will take, I just showed you it would take 100 seconds just to do the first decision of which depot and what's the first pickup. If I put all of the decisions in here, I'm actually going to find that it's going to take about 1,100 seconds if I had 10 depots and 100 pickups and drop-offs, even with a good find path. Okay, and we're only going to give you 50. So this is way too big. So that's too slow, but we've already had a suggestion of what we could do that's smarter. We don't need to use find path to evaluate the travel time between every pair of points we're considering. So we could approximate it with geometric distance. So we could say things that are close together, we can probably get between faster. So we're not going to call find path every time we want to estimate the travel time from A to B. We're just going to use the distance between them to estimate it. Okay? So if we do that, our algorithm is still n squared, right? Still this d times n plus n squared, but we basically reduced the constant. Our constant used to be 0.1 seconds to figure out, what's the travel time between two things, which was the key operation we're doing. Now we can do that with just a few computations. So it's going to be more like 10 to the negative 7, which means this is going to take maybe a millisecond to do the whole optimization of what is my delivery order. So that's more than fast enough. You got 50 seconds, you figured out your delivery order in a millisecond, you're great. Okay, now that's not the final answer because you're not asked to just return a delivery order, you're actually asked to return a path that connects everything. But once you have the delivery order, and these problems I've given you, we've got 100 pickups and drop-offs. So we've got about 100 paths defined between intersections once we've chosen the order. So that's 200 calls to your find path. If your find path takes 0.1 seconds, that's only going to take 20 seconds, so that's fine. Okay, so once you've chosen an order, hooking it all together with your find path algorithm is not that bad. It's if you're invoking find path over and over again as you're trying to decide, is this a good order or not, that you're going to get into trouble. So you can avoid that by just approximating the travel time with some function of geometric distance. Does that make sense? Okay, so it's going to speed things up. Okay, so now we've got a realistic way to make this algorithm fast enough. And let's just walk through what it would do. So we found this is the shortest path from any depot to any pickup. So we're going to do that first. From this point, what that algorithm did is it said, just immediately drop it off. Don't think about it, just drop it off. So we go to here and drop it off. Then we decide, okay, what's the next pickup, what's closest, and this one's closest. So we're going to go there, and then we're going to immediately drop it off. We're going to go way out here. Then we're going to go, what's the closest pickup after that? It's going to be here. So we're going to go, whoops, maybe we've decided to go there. That's what I did on the slides. Then we'll drop that off, and then we got only one pickup left, so we're for sure going to pick it up now and then drop it off. And then we'll go to whatever depot's closest. So say that one. So it's a lot better than random. Although we do have this back and forth on the 401 that still seems a bit wasteful. And the idea of how to improve more, D13 already told us. Okay, so D13's proposed algorithm was already smarter than this. They didn't say go to the next pickup, they said go to the next legal thing. Okay, so, and that's not much different. The code is not significantly more complicated. So we still start off by saying, okay, find from every depot to every pickup what's the shortest. Let's do that. And then as long as we have packages to deliver, go to whatever the next legal thing is. So it might be pick up a package, or it might be drop off one of the ones we already have. Do whatever's shortest travel path, and then at the end, go to the nearest depot. We work out the complexity of this. It's not much different, right? So it's order D times N for the first, find, look at all the possible depot to pickups, that's D times N choices. We're gonna go through this loop now 2N times, and in each one of them, we're gonna go, what is our nearest legal pickup or drop off? That involves going through basically N to 2N things, so it's also order N. And then at the end, we're gonna drop off at the nearest depot, so that's order G. If you get the complexity of that, it's the same as before. It's D times N plus N squared. There's a little more work you're doing, so the constant's a little bit higher, but not very much more. So this is a better heuristic, and it's not going to be much slower. Okay, so if we did that one, we'd still start off in the same spot, go to the first pickup. But now we evaluate not just going to drop off that package that we picked up, we also see maybe there's something to pick up on the way. So we'll actually go pick up the second package. After that, we'll drop off that package because it's nearby. Then we'll pick up that one, and then we'll go drop off the packages kind of in a logical order. And we actually wind up going back to a different depot than we did before because we're on the opposite side of the city. And we do less back and forth travel. So in this example I gave you, it's actually quite a bit shorter, this small change in the code. Okay, so both of those heuristics are greedy. They make the next decision without thinking much about the future. So they make the best decision they can make right now, just looking one step ahead, and they never go back and change a decision. So greedy algorithms are generally fast, but they often don't get the best solution. In this case, it doesn't get the best solution. There are a lot of variants you could make on greedy algorithms. So you could use right now, the algorithm we just did is only looking one step forward. What's the best decision what's the closest thing I could get to that's legal? You could add in smarter, additional intelligence to it, where it says, well, if I do that, what happens after that? So maybe I should take that into consideration too. Try to look 2 steps ahead. So you can do that, and you can make greedy algorithms that are a little bit smarter. Okay, and that's as far as we're going to go today. So that's kind of our first class of algorithms. Greedy algorithms, fast, not too hard to code, can get reasonable answers, so they're not bad, but generally will not get the best answers. Okay, thanks.